large language models are going to have infinite context windows or trillion token context windows and very, very fast instant reasoning. They can reason entire book of ideas in an instant. So now we will learn a big part of that step by step. So this is just Mamba, and it's a mechanism to have a linear scaling with sequence length. It's a way to compress tokens as opposed to quadratic scaling of the transformer. And it can actually be used together. Some layers transformer, some layers Mamba in a large language model. So this is an interesting path to research. I showed some research I did last video, but now we need to understand how Mamba works. We already know how transformer works. I have my large language model in one of the videos. You can check this video. So now let's understand this part. This is just about learning and understanding and coding it from scratch. First, we're gonna have these imports, torch and numpy. Now understanding the core state space models. Mamba is based on state space model. The core idea is we have a hidden state that evolves over time. This hidden state is a compressed representation of all of the previous tokens text. So only the main ideas or information and discarding all of the details from the previous text that we don't need, that are unnecessary. Because we need to solve quadratic scaling of attention, that's too much. And also we can use this by DeepSeek to solve quadratic scaling. This is gonna solve it, or research on top of this, but for now let's just understand this Mamba part. My idea is to combine Mamba and native sparse attention, but let's see Mamba now. And if we solve this sequence length, we can feed raw bytes into the LLM or VLM. This hidden state gets updated based on input, based on tokens. Output is produced from the state. Now let's see this part. Let's create a simple sequence. Think of it as 3 words in a sentence. These are 3 tokens, 1, 2, and 3. It could be 3 words, for example. Then adding a memory bank. In Mamba and all state space models, we have a hidden memory bank called the state. Let's create one. State size equals 4. Our memory has 4 slots. So we will start with empty memory by saying torch zeros state space. We will just create an array of 4 zeros. Think of state as 4 empty boxes where we can store information. Initially, they are all zeros, empty. Part 4. How does information enter the state? We need a way to put information into our memory. This is what matrix B does. We will create a random matrix of state size rows, and each row has just 1 element, so we have 1 column and 4 rows in this case. This is similar to weights in neural network, when you multiply input with weights to get output. But if you don't know, it doesn't matter. We'll see. So what does B do? B is like a gate that decides how the input enters each memory slot. Because these are some numbers, when we multiply them with input, depending on the input, we're gonna get some results. So this matrix B is gonna transform input. So whatever the input is, this matrix will transform it in some way, so the result will be reactive to the input. So B is a gate because it controls how the input is transformed and how it enters the state. Because we are multiplying B and input, for example, if we have some large numbers in B, then the result will be a large number. Or if we have some small numbers, then result will be small. And also, if both B and input are large, then the result will be very large. If one is large, one is small, then it's not going to be so large. You see how B controls how input is transformed. Let's see an example. Input value, we're going to take the first number of the sequence, which is going to be number 1 of our sequence. And then new information is B times this input value. So now this input value is scaled by B. Remember, B is just 4 random numbers right now. It's just an example. So in this case, we just multiply each number with 1, so we get the same numbers. What happened? We took our input 1 and multiplied it by B. This creates 4 different values. one for each memory slot. Some slots get more information, some less, depending on B's values. So by more information, I suppose this means bigger numbers. Because remember, our actual data is number 1, but B can make this number smaller for slot 1, can make this number bigger. So now this is going to influence slot 2 more than slot 1, where B made it a smaller number. And remember that the amount of numbers we have in B is same as our state size. So in this case, for every slot in the memory in state, we have one number in B to multiply the input. So to summarize, this B is going to transform this number 1, make it bigger and smaller depending on each slot's corresponding B number, which is same as making this signal or this information stronger or weaker. Part 5. How does memory persist? Memory shouldn't just be replaced, it should evolve. So when you have new calculations, they shouldn't just replace the old ones, they should interact with old ones, be multiplied with old ones, etc. Matrix A controls how much old memory we keep. So here we have matrix A. So we're gonna just say we keep 90% of the first memory slot, 80 of second, 70 of third, etc. And that's what it explained here. So values close to 1, we have long-term memory. It's remembering a lot of the past memory. Values close to 0, short-term memory. They are useful for different situations. Maybe you need to remember a lot, but new information is not so important. Sometimes latest information is more important than something far away. Now the key SSM equation, updating our state. State is equal A times state, so this controls how much to keep of the previous state, plus new information, dot squeeze, we'll see what this is. I explained this already, I think it's clear. We also have this matrix C, and we use this when we read from our state, when we want to get information from our state. I know it's also confusing to me a little bit, but this is not used for calculating the state. This is used when we read from state to use for neural networks or something. So we do dot product between C and state, which will give us a single number. C decides which parts of memory to read. If C0 is large, we pay attention to memory slot 1 because we're doing dot product. So we multiply these first two, second two, third two, and we sum up all of the results, the products. If C2 is 0, we ignore memory slot 2. The output is a weighted combination of all memory slots. Part 8, let's see processing the full sequence. Let's process all 3 elements. So let's create variable for outputs. Let's reset our memory, so we just create new 4 random numbers in our memory, or sorry, 0 zeros. Now we go through our input sequence. Our input sequence is 1, 2, and 3. So first, we look at the first or 0th element in that input sequence, which is element with value 1. So that's current input. This is a scalar, a single number. So new information is B times current input. And example B could be 4 elements, 1, 2, 0.5, and 0. As I said, what B will do is it will transform this input 1 into some, either amplify the information, or make it weaker, or erase information here. And as you can see, B is shape 4, 1. So you have 4 arrays of 1 element. So when we multiply this with this input 1, we're also gonna get 4, 1. So we need to unsqueeze this last dimension. So instead, we just have 1 array with 4 elements inside, not 4 arrays like here. So this is why we will unsqueeze. So new info.unsqueeze, we will remove this extra dimension. So we will just have 1 array with 4 scalar elements. You can check this in Google Colab how it works. So after squeeze, it will be one array of 4 elements. Now it's a 1D array matching state shape. Now it's same shape as state, our memory. So then state is equal to A times state plus new info. So A, as I said, says how much of the state we keep. If A is 0.5, 0.5 all the time, so we just keep half of the previous state and then add this new information. So now we will have this new state. It will show you calculations here manually as well. And now we have this output we are reading from the memory. So this is another C matrix. This will tell us what information we will read. Let's say C will read first but ignore second, and then read third and ignore fourth. So when we do dot product, we will have this as the result. So we will just have 1 plus 0.5 because those two are kept. And these can be different numbers here as well, so you will get different dot product. So C just determines how much of each you keep, and then we add them up all with dot. This is the formula, what I just explained, of dot product. Then we go to the second iteration. Now we're processing element 2. I is now 1, so we just take sequence element index 1, so that's 2. And we do the exact same thing. You will notice how this is being processed sequentially, element by element. And also we had some memory before, old state, that we calculated, and then we say A times old state plus new state. Now this is the new state, new memory. By the way, if you want this well explanations, you just prompt Opus 4.1 thinking to do these small blocks and then show example numbers step by step. Don't write too much code, just do markdown tutorial, this kind of prompt. And then what makes Mamba unique? Because this is state space models in general, what we just described. So Mamba has selective, I don't know what, but something selective. Okay, part 1, the problem with fixed matrices. Let's see why fixed B and C are limiting. Let's say we have two very different inputs. So number 10 is going to be some very important word. For example, not in not good. If you don't have this not, if you don't see it, then you will think completely opposite, which is wrong. Not is very important in this not good words. And the, for example, is a lot less important word. So not will be 10, the will be 0.1. For example, this is just example. And let's see what happens. With fixed B traditional state space models, we have some fixed B, and then we say B times important word, we get 10.25.0 as the calculation. So actually the important word gets processed the same way as boring word, just scaled. So boring word will have same numbers, it's just gonna be 100 times smaller. Problem: the model can't choose to store important words differently. It just scales everything the same way. So the difference between these numbers is just linear, and model, all of the complex information in the world, model has just like, can just multiply like 2x, 3x, 4x, the same thing, to represent all of the complex information, which is not gonna work. You need a lot more, you need to give model a lot more freedom and ways to represent information, not just to multiply it by 2 times, 3 times, 4 times, etc. So Mamba will make B input dependent. It will depend on the input. So we have a linear layer. It's called make B. So this will create B based on input. So this 1 is dimension of our input and 4 is the dimension of the B. So this linear layer will convert our input, 1 number, into 4 numbers of B. So this linear layer, these weights are gonna learn to create B depending on the input. So input is represented well later. Let's manually set weights to see this effect. Let's say these are trained weights by our neural network after training. Then the input will get transformed differently, each input differently. It will not have same B matrix. To be honest, this rest of tutorial is a bit confusing, so let's go to perplexity. All three of the matrices A, B, C that we talked about are input dependent in Mamba, so there are learned weights that will transform input into A, B, and C, so they are dependent. There is also this D matrix that's directly converting input to output without going through the hidden state. Not sure when this is used. I see. So the output of a state space model at any time step is typically a combination of the transform hidden state via matrix C that gives us the output, and then plus possibly the direct contribution of the current input. So this is like a residual connection that keeps the current information. So we take current and sum this transform with memory. We have this in transformers and in UNets, etc. It's just to make sure that this information that goes through state is not transformed too much and we don't lose information. So in this residual connection, we keep information. So the output, actual output, can be C times state plus D times the input itself. Even though we use the input to create the state as well, we also want this to keep more information. And all of these are learned and dependent on input itself. So these are also generated, C and D and A and B. But sometimes we don't want this, we just want to depend output on state. Now the second part, very important, how do we parallelize Mamba? Because we are calculating it sequentially, state by state by state, so each state depends on the last one. So how do we make it parallel on GPU? Like attention mechanism can be parallel. And that was the issue with my implementation here. It was taking too much time because 5,000 steps in pure attention transformer take like 4 minutes. But in this sequential Mamba 2, it takes like 4 hours instead of 4 minutes. Even though there is less calculations, but they cannot be done parallelly or until we implement Mamba 2. Let's understand how Mamba 2 does it parallelly. The key innovation in Mamba 2 is that it can be computed in two mathematically equivalent ways. SSM mode, sequential recurrence, hard to parallelize. Attention mode, matrix multiplication, GPU friendly. So we learned that in Mamba we go through the sequence and we multiply A dependent on that current input times the state plus B dependent on current times the current input. And then the output will be that C matrix dependent on the input times the state. That's also dependent on input. This is what we've been learning until now, the whole video. So if you don't get it, just go back a little bit and try to understand it. This is inherently sequential. You can't compute this state age of t until you have the previous state, age t minus 1. This is the crazy thing. At time step n, where you need your state n minus 1, the previous state, you can actually skip and calculate that state directly in that time step without needing to sequentially calculate every state before. So you can just mathematically take all of the formulas, take parts of all of the formulas before all of the steps, put all of the parts into this step and calculate all at once. At first, this seems like more computation. For every step, we need to calculate everything until that step, but in reality, this makes it parallelizable on GPU, so this is going to be a lot faster. Now each step is independent from the previous step. Now we don't need to sequentially calculate every previous step. Now we can calculate every step just by itself. We will understand it better by seeing this example. At time 0, the first input, our hidden state is 0, we don't have anything. At time 1, our new hidden state will be A, that's dependent on the input at time 1, times previous hidden state, plus B dependent on time 1, times input. And since this is 0, then it will just be B dependent on input 1 times input. Let's see for time 2, and there will be a pattern here. Look at the pattern. A2, so A dependent on input 2 times age 1 hidden, the previous hidden. And this previous hidden is actually our B1 times age 1 times x1, sorry. So we don't actually need the previous hidden. We just need our B, which we already have, and our input, which we already have. So we don't need to calculate the previous hidden state in reality. And this is the most important thing. From now on, this pattern will start to repeat. We will just be replacing the hidden state with some version of the previous output of B and X, which we both have at all of the times. Let's see the next iteration. So we have age hidden state 3 is A3 times age 2, the previous, and age 2, it's this. So we just multiply this age 2 with A3. So we get A3 times first part of age 2, which is this. So we got A3 times A2 times B1 times X1. And then A3 also multiplies the second part here, B2 and X2. So A3 times B2 and X2. And this is the last part here. So we see the recurrence here. Now we don't need previous state. We can just calculate this at the beginning all at once. Now we want to discover a pattern. So this is the pattern, but we will understand how we got to this. So this shows how much does information from position J affect position I. So we multiply, starting from A of I, input I, and then going back to the J plus 1. Let's see on an example how we get this. Let's say we got 4 inputs, so A that scales hidden state and B that scales input all have 4 elements. Starting at first input state is just B of 0 times input, let's say 1. Second one, we got scaling the hidden state, and then B of second input times second input. Time 2, we scale the previous hidden state and add the current input processed. Now let's see where each input contributes. Let's expand H2 to see all contributions. Guys, I find this a little bit complex, and also I'm a little bit tired, so I think that will be it for this video. I'll make more videos about implementing this in code. This is my code, and still it's not parallel. It works, but it's not parallelized for some reason. So we need to just understand all of this. Check out other videos on my channel, and see you next time.